In this section, I want to talk about a feature that I think is probably the single most used feature in Wireshark, and that's the ability to follow packet streams. Now, the best way to talk about packet streams is to actually demonstrate the value with an actual packet capture. So I have here a file called mailsender attachment.pcapng, and we'll go through this capture more in detail when we talk about the SMTP protocol later. But what we have here is a mail client sending a file or sending a message with a file attachment to a mail server. And we're doing that using the SMTP protocol, which rides upon TCP as its transport layer protocol. So we can kind of see that going on here. You see we have first a three-way TCP handshake, send, SYNAC, ACK, and then we have SMTP data going on, which is going to represent the mail message. And you can see in the info column, you can see mail from, receipt to, data fragment. You can kind of see what's going on. Now, we can actually click into this. And if you look down here at the packet bytes window, and I'll go ahead and bring this up, you can see that we have some clear text things happening. So we see EHLO 172.16.16.22. I can scroll down to a couple other packets. We see, looks like maybe some SMTP commands here. We see 250 mail 01, 250 pipeline, 250 size. We see some different things like that. I can continue to scroll down and we see more of this. So we see PPA at skynet.local. So we see mail addresses, we see data, we see carriage returns and line feeds. Here we actually see some names and we see some message content. So there's a lot of information to be had here, and that's because SMTP in this case is clear text, so the data is not encrypted, it's not really obfuscated, it's all there. Of course, we can't send all that data into one packet. Packets are limited to a specific size, so the data is being broken up across multiple packets, and TCP and IP are being used to deliver that, of course with TCP being used to ensure reliable delivery. Now, the question becomes, how can we view this data all together, right? Because if we just went through and just started scrolling down, kind of like I've been doing here, just scrolling up and down, that's kind of cumbersome. And this is a relatively short capture. It's only 58 packets, but in a lot of cases, they're going to be much longer, right? You're going to have to deal with a lot more data. So it doesn't make sense just to scroll as we are and just kind of piece it together from the packet bytes window. Not the best way to do it. Now, the cool thing is Wireshark provides an ability to do this for you with its following stream capability. So when we talk about streams, what we're talking about is extracting the data from these packets. So basically extracting application layer data from these packets and reassembling it in order all together so you can view it all at once. And that's a pretty powerful thing. So let me demonstrate to you how powerful it is. What I'm going to do here is right click on any of these packets, go down to follow. We have a couple options here, but only one is highlighted, and that's for TCP stream because we're looking at TCP data. If we were looking at UDP or SSL or HTTP data, those options would be available as well. But we're looking at TCP, so we're going to go ahead and click that, and we're going to be presented with this window, which is showing us the reassembled stream that's pulled out of all of these packets. The first thing you might be saying is, wow, this is pretty cool. And it certainly is, because it really makes the process of reviewing the packet payload data a lot easier, right? You can very easily see we have a lot of cool clear text data here. You can even see we actually have email content down below here, which is pretty neat. So we're actually looking at the content of this email and everything associated with it. But there's a lot more going on here, and I want to describe this window a little more fully. Now, one thing you might notice immediately is that we have a couple different colors going on here. So this first line is blue and the next line is red, then the next several are blue. And what that's actually indicating is the direction of the traffic. So we're looking at bidirectional traffic where we have a mail client and a mail server, and they're communicating. We need a way to distinguish what's from the client and what's from the server, and that's what these colors are doing for us. Now, the question becomes, red and blue, which one is client, which one is server? And we can find that answer by looking down here at the bottom of this screen. And it's kind of small. It's kind of hard to see, but it says 26 client packets, 8 server packets, and 15 turns. And what that's telling us are that you notice how where it says client, that's in red, and server, that's in blue. So what it's saying is anything that's in red is from the client, and anything that's from the server is in blue. So that means the first line here, this 220 mail01 ESMTP postfix Ubuntu, is from the server. The next line at red is from the client. The next several blue lines are from the server, and so on. Right, so this makes sense. Even without fully understanding how SMTP works, you can see what we have is the server in the first line is sending its banner saying that it's running a postfix mail server on Ubuntu. The client connects with its IP address. The server sends these next several lines saying the features it supports, such as TTLS and a certain size limit. Then the client begins sending the emails. So it says, mail from sanders@skynet.local. There's an acknowledgement. Mail to ppa@skynet.local, another acknowledgement. And then we see data being sent. And of course, in red here, we see the actual mail message being sent right here in red. So the red and blue help you to determine the direction of the traffic, which is pretty darn cool. Now we're looking at both directions right now, but you can actually filter that too. If you go down here and click this bar here where it says entire conversation, 77 kilobytes, you can click that and you see we have the options for traffic direction both ways. We can look at 280 bytes going from just from the server. So these are things that are just sent from server to client. Or we can go the other way and look at things just sent from client to server, which is useful if you're only concerned about one direction of traffic. So for instance, if you're looking at a bunch of emails sent to the same server, a lot of the server traffic is probably going to look the same. So you can actually just limit this to client traffic to actually view the content of those emails, which is pretty darn neat. There are a couple other things going on here as well. You may have noticed as I've clicked around in this packet capture, things are changing behind me. And what that's doing is whenever I click a certain section, that's linked to the packet list window behind me, and it's highlighting the packet that data is contained in. So right now I clicked to this ELO and it's showing me that's in packet 5. I'll click down here and this is where it says data. It's going to show me that's in packet 12 and so on. So it's going to be linked there, which is really nice. If you see something interesting in the stream view and want to find the actual packet associated with it, you can do that here as well from the assembled view. Now we have a couple other options that are unique down here at the bottom. We can find things if we need to. So I can go ahead and type in here, JPEG, and it's going to highlight here down below where it looks like a JPEG image was attached to this email. Of course, that content's here below. It's base 64 encoded, but we have that available if we wanted to pull that out and actually carve the file out and actually reopen it. It's all right there. So this JPEG image we could actually extract fully and view it. We're not going to do that here. This packet capture is going to come up again later, and we're going to do that process then. But know that this is the way we would get to that data. So that's pretty darn cool. And we have the ability to find things within it as well. Of course, we have the ability to show the data in different formats. We're looking at it in clear text ASCII right now. I could choose to say, let's show it in a hex note. And then we're going to be looking at it in a format similar to what we would be seeing in the packet bytes view. But again, just the payload data extracted here for us to view kind of in sequence, which is pretty neat. I'm going to change that back to ASCII. Now we have the ability to print these things out, also to save them, which is pretty cool. And saving them is how we'll get to the point of doing packet carving later, which is pretty neat. One of the things I think is pretty cool here is this stream option. So it says stream 0. And what I can do here is click the up or down button to go to different streams. So instead of, if I'm looking at stream 0, if I want to find stream 3, instead of going into the packet list window and having to find that packet, finding a packet that exists in that stream and then doing that or typing a new filter in the filter bar, I can actually just click the up arrow a few times to get to stream 3 without leaving this window. That's a relatively newish feature and it's really, really valuable. The packet capture we're looking at now only has a single stream in it, and those streams start counting from 0. So it's not going to do me any good to click it now. But know that it is available, and it's a really nice way to pivot between different streams within your packet capture. So that's pretty cool. Very last thing on this window worth noting is notice behind us that when I clicked this, it applied a filter for TCP stream equals 0. So when you right-click any packet and tell it to follow the stream, it's going to bring this window up in the foreground, but in the background, it's going to apply a filter showing only that stream. So just important to be aware of that if I were to close this window out and go back, then I'm not looking at all the packets here. I'm only looking at a single stream. Of course, this packet capture only contains one stream, so you see we have 58 packets total and 58 displayed. But if there were a couple of different streams in here, I would only be looking at stream 0, and that is what happens when you follow any stream, is it's going to automatically put that filter in. So make sure you clear that if you actually want to see everything that's in the capture. So now I've pivoted over to a different capture file. This one's called EK to CryptoWall 4, which is one we're going to look at later when we go through a security exercise. It's not important to really fully grasp what it does now, but I think it provides a good example of another way we can follow data streams within Wireshark. Now we see here we have what appears to be an HTTP connection, so a web client browsing to some type of web server. We see that we have TCP data here initially. We see a send SYNAC ACK, a new connection being set up. Then we see a GET request for index.php/services. So really looks like we have HTTP data going on. So I'm going to go ahead and let's just click on one of these random TCP packets and let's follow the TCP stream the same way we did in the last exercise. Now I've done that here, and you see we have some useful clear text data. So we're looking at the red data first, which is from the client. We see a GET request. We see refers. It looks like this was referred from a Bing search. We see user agents. We see things we would expect to see in the HTML header. Following, we see the response from the server. In this case, we see the clear text response. It looks like it was received successfully, so we got back a 200 OK with some various information. Now, the interesting thing comes below this. If we look, we see a bunch of data that's really unreadable. And that's kind of surprising because HTTP is a clear text protocol. We know that when we're browsing with HTTP, the data should be visible because it's unencrypted, unsecured. It's only with HTTPS or some other type of additional encryption that data would be truly encrypted and hidden from us. So why is the data we see here not visible if HTTP is a clear text protocol? Well, the answer relies in this section right here where it says content encoding gzip. So we'll see right before that, when the client makes its request, it says it will accept the encoding of gzip, which tells the web server, hey, if you want to zip this data up and send it to me that way, so it's a smaller amount of data and more efficient on the network, I will gladly accept that. And the server kindly obliges and tells it, hey, the content I provided is in gzip format, and meaning that the client within the browser would have to expand that data back out, right? So that's exactly what's happening here. The data we're seeing that's unreadable is unreadable because it is gzip encoded, because in this case, Wireshark has not expanded that data. It has not decoded it and made it visible here. So the downside is that's not very helpful to us. Without it being decompressed, we can't see what it is, we can't analyze it, and that's unfortunate. We need to be able to do that. So the good thing is Wireshark does allow you to see this decompressed data, but you have to get about it a little different way. Remember, we just clicked on one of the TCP packets and told it to follow a TCP stream, which works for most TCP traffic and gets us part of the way here. But we need to go a little bit further. So what I'm going to do is close out of this, and instead of picking one of these TCP packets identified by the protocol column, I'm going to pick one of the actual HTTP packets containing HTTP commands. When I do that, I'm going to go to follow. Instead of going to TCP stream, which is still an option, I'm going to go down here to HTTP stream. Now you notice we have the same window, but in this case, all that data that wasn't readable is now readable. So what we're doing here by following HTTP stream, that's telling Wireshark to look for gzip encoded data in the stream and go ahead and decompress it and make it visible to us. And that's exactly what it's done. So we see here we start out with an HTML style tag. We have a bunch of things here that are not super readable. They are in plain text, but they're kind of obfuscated. And that's because this is a file where there's some bad stuff going on and the attacker is intentionally trying to hide things from us. We'll talk about how that can be decrypted a little bit later. But I can scroll down here and I'll eventually find some things that are a little bit more familiar. So here we go. So here we have an HTML tag. We have a head tag. We have meta tags, titles. Here's a title tag, etc. So we have things we expect to see in HTML data. We see style sheets, we see all those different things. So the key thing to take away here is that by following the HTTP stream when encountering HTTP data, we're able to decrypt that gzip, or not decrypt, but decompress that gzip data and view it. So make sure when you're doing HTTP data, you follow an HTTP stream and not just a TCP stream if you're concerned about the payload information, because it's the only way that you're going to be able to get it out of here. I want to cover just one more quick example before we call it quits on streams. And in this case, I've just captured some packets while browsing to encrypted.google.com and browsing over HTTPS. So if you look over here on the right, you see we have a TCP connection set up over port 443, and then we have TLS data here, which is indicative of SSL over HTTP or HTTPS communication. So encrypted HTTP, which by default, unlike our previous example, is not going to be clear text. It's not going to be something I read. So I can actually right click in here and go to follow TCP stream. When I do that, you'll see there's a little bit of clear text information when we're looking at the certificate exchange that goes on, but very quickly I get into a bunch of completely unreadable data that is actually encrypted to a point where I can't see it. Now, with encryption, by design, you're not going to be able to see this data unless you have the required materials to decrypt it. So unless you have the required keys or the required server certificate, you're not going to be able to do that. But if you do have that information, Wireshark does allow you to use it. And I want to show you real quickly where that goes. If you go into Edit here and then go to Preferences, which is a screen we're pretty familiar with by now, there's a Protocols section. And the Protocols section contains basically all of the Wireshark dissectors that are configurable in any way. So it's going to have sections for a lot of protocols you know, and many, many, many of them that you don't. And that's okay. There's a lot of them I don't know either. But there is a section for SSL here. If I click that, you'll see I have the ability to reassemble SSL records spanning different segments. That's on by default, but to make that work, you have to provide a list of RSA keys or pre-shared key, whatever the configuration of your server is. You need to provide that shared secret, that local secret to the server to be able to decrypt that. So if you have that, depending upon your server configuration, that's going to vary a little bit. But if you have that, you can input that here. And once you've input it, I'll go ahead and click OK here. You can go back here to follow and choose SSL stream, and the data should appear in a decrypted format. In this case, I don't have the server certificate for google.com, as I shouldn't. So we're not actually decrypting anything. There's nothing to see. But if I did, Wireshark would decrypt that data for me. So this is really going to only be applicable in a couple situations most of the time. One of those is going to be when you're dealing with your own infrastructure and it's someone, maybe one of your own clients, making an encrypted connection to another internal server, maybe a payroll server or some type of local web application. You should have your own certificates then because you set them up yourself. If you want to load those into Wireshark to decrypt that traffic, then you can certainly do that, and it'll appear when you follow the SSL stream. Another example is maybe when you're dealing with malware that does some type of encrypted communication, and maybe the malware command and control has been compromised by the good guys at some point, and you have that certificate so you can decrypt. If you have that certificate of those keys and you want to be able to decrypt at that point, you can do that to understand the malware traffic or the malware communication a little bit better, which is certainly helpful. So following SSL streams is possible if you have the right information. So I want to put that out there so you're aware of how to do that. So with that said, that's going to bring us to the end of our discussion on following streams in Wireshark. Again, this is really probably the most used feature within Wireshark I see people utilizing, just because it is a really quick way to get to the data, and that's really what analysis at the packet level is all about a lot of the times. There's really just a very small amount of data you're going to be making a decision on, but getting to that data and getting it visualized in a way that makes sense is often the hardest part, and following TCP streams or UDP streams or HTTP streams or so on is really one of the best ways to get that information to you in an easy to read manner, because you're reassembling that extracted application layer data from all these packets. So I want you to get really familiar with following streams. We're going to follow a lot of them as we go through other examples. It's a very practical thing we'll do quite a bit of. So I want you to get familiar with that, capture some of your own packets, look at the various protocols you have going on, and start following streams and see what you can get out of them. I think you might be surprised at how much information some will provide and how little some will provide where you might expect more. So get used to that, because we're going to be doing it a lot more as we go on and go through a lot of practical exercises.